Okay, hello class. Let's move to the application related to the solution thermodynamic. Okay, previously we have covered the solution thermodynamic in theoretical aspect. What is the criteria or the properties that we can introduce the composition in the, especially related to the multi-component. In this topic, we will move to the application of the equation that we have learned in the theoretical part. Okay, for in this topic, divided into two parts. Okay, for the first part, we will cover on the application of the excess Gibbs energy. How do we determine the excess Gibbs energy, and what is the empirical equation related to the Gibbs excess Gibbs energy from the vapor liquid equilibrium? And then for the second part, we will move to the ideal solution related to the mixing process. Okay, from the previous chapter, we have learned about the theory of solution thermodynamics, that the decomposition can be introduced from the chemical potential of denotes by mu I equal to the in determining the chemical potential is based on the energy transfer or Gibbs energy due to the changes of mole composition of component I at constant temperature, pressure, and the other composition that component I. And then we been introduced the fugacity or the measurement of the capability of the species to expand or to be transferred from one phase to another phase based on the pressure on the species. And then the fugacity coefficient also be introduced to determine the ratio between the real and also the ideal process. And we also have been introduced the activity coefficient in the solution in the liquid. Okay, for the fugacity and fugacity coefficient, we cover on the pure species, which for the pure species, we can determine it whether in liquid or vapor phase. And for the gas mixture, we already defined that at equilibrium, the fugacity for each phases are the same. And we also learn about the ideal solution. How can we express based on the excess properties in the ideal solution? And then in the excess property, we have been introduced the Gibbs excess properties in our calculation. Okay, in this topic, we will move to the application related to the excess property of excess Gibbs property. First, we will proceed with the identify what is the learning outcome in this part. Okay, in this part, we have three main topics. First, we're gonna learn about the liquid phase properties using the VLE data. Okay, previously we have learned about the vapor liquid equilibrium data based by having the pressure versus SY or mole fraction, or we fix the temperature or we fix the pressure and vary the pressure against the mole fraction. Okay, in this topic, you should be able to determine the fugacity, activity coefficient, excess Gibbs energy from that list of the data set, and then application of data reduction from the VLE, such as Margus equation and also the Van Laar equation. Okay, the second topic is to relate to the model by using the model for the excess Gibbs energy. You should be able to determine the activity coefficient through the model from excess Gibbs energy, such as the given model or the equation, which we focus on the Margus equation and Van Laar equation. And then the last, we will we will move to the local composition model using the Wilson and RTL unique and unified. Okay, this local composition model usually being used, or we can use this model using a simulation tool. The calculation method is a bit complex, so we will only you will only be introduced about this model in this topic. Okay, these are the overall the application of solution model. We have learned about the fugacity and the introduction of the activity coefficient in the expression of fugacity and the curve of fugacity by introducing the Lewis-Randall law to the fugacity of the species in ideal equal to its small fraction, and we can compare it with the Henry's law. How can we compare between both? And then second topic we will cover on the model of Gibbs energy. We have the Raoult crystal, which we're gonna expand it to categorize it into the Margus and Van Laar. And for the local composition model, we have Wilson and RTL unique and unified model. Okay, the last topic which cover on the second part. Okay, we're gonna learn about the heat of mixing by determining enthalpy of mixing and also the excess enthalpy in the heat of solution. Okay, the first part is fugacity. Okay, I hope that you still remember about the fugacity that have been introduced in the previous chapter. Okay, the fugacity in equilibrium, we have this the species in the solution, in the vapor phase and also the liquid phase. Okay, in equilibrium, we're gonna have the same value of fugacity, and it gives the fugacity coefficient of vapor phase can be easily determined equal to 1, and then the VLE measurement usually at lower pressure or pressure less 1 bar. So vapor phase will be assumed as in ideal gas. The fugacity of species I for both a vapor and liquid equal to the partial pressure for species I in the vapor phase. So we know that for the infinite dilution, or if we have the two phases, whether liquid and vapor, it equal to the, it gives the value or relate to the saturation pressure. Okay, the fugacity for species are equal to the partial pressure in ideal phase that give us the Lewis-Randall rule. The fugacity value increase from 0 when the vapor phase for species are to the saturation pressure, which at vapor phases equal to 1. The activity coefficient is being introduced when we deal with the solution or the liquid or the species in a solution, that it gives us the concept of Lewis-Randall rule. From this, based on the Lewis-Randall rule, the fugacity of the species in ideal solution equal to its small fraction. So these are the definition or the concept of Lewis-Randall rule that applicable at same temperature, pressure, and composition. Okay, by simplify this equation, we can compare it with the modified Raoult's law. If you can compare it, introduction of the activity coefficient, and then okay, this is for both actual and ideal solution fugacity. We can replace it to the modified Raoult's law because it a measurable quantity compared than using the Lewis-Randall rule to solve it. And then we can conclude that the activity coefficient or can be determined by using the modified Raoult's law in the solution. Okay, so we already covered it. This is just to prove that the the fugacity or based on the Lewis-Arundel rule can be replaced using a modified Raoult's law. Okay, example, if we are given the set of data of vapor liquid equilibrium data, so we have the example here, we have the pressure versus the mole or the mole fraction, so P versus SY. So if the S or the composition in the liquid phase can be determined, we also can obtain the composition in vapor phase. Okay, from this data or VLE data, it will give us another additional data known as the fugacity of the species in the solution from this partial pressure. And then by inserting this value, or you may determine the fugacity using this equation, so we can obtain the fugacity of species I in the solution. And then after that, we can also determine the fugacity of another species by using the same equation, but you may replace it from y1, you may replace it to y2, because we know that y1 plus y2 equal to 1. At the same time, we can obtain the value of activity coefficient of lambda using the modified Raoult's law. Okay, this is another additional information that you can extract, or you can evaluate this data to obtain another data such as fugacity of the species in the solution, as well as the activity coefficient. Okay, by using that data when plotting the fugacity versus against the composition, we can have the two data. The first is based on the component 1, component 2, and the second is based on component 1. So you can see that from this data, we can have until it reached the x1 equal to 1, that means x2 equal to 0 for the straight line. This is the straight line, or the dotted is for the ideal solution that follow the Lewis-Arundel rule. And then the data obtained from the VLE, from the calculation, we can determine the P1 saturation, because the saturation pressure at component 1 equal to its pure species, or that respective component will be equal to 1. And then same goes to the second component. We can obtain the value of fugacity equal to the saturation pressure of component 2 at its pure component. That means x1 equal to 0. We can obtain the x2 equal to 1. Okay, for the second graph, when we plot, it can be equivalent, or we can equivalent this data based on the law that we have learned. Or first, we have Henry's law at the one species is the saturated compared than the other species, and then the second line here is the Lewis-Arundel rule. We can obtain that for the Lewis-Arundel rule, it covers on the species equal to 1, and for the Henry's law is only applicable for the diluted species. Example, for the species 1 equal to x1 equal or near to 0 in diluted solution. Okay, for based on this graph of the acetone, okay, when we plot the fugacity of the acetone in the solution against its composition, okay, it's referring to the Raoult's law. And then at x1 equal to 1, or at acetone equal to 1, we can obtain the fugacity of acetone. Okay, the positive deviation, or when the curve Fi, or the solution fugacity of the solution versus component is above than the Lewis-Arundel line, so we can obtain the positive deviation. And then the negative deviation, that means we have the produce the line lower than the Lewis-Arundel line. And also this is the Henry's law, which apply to the species approaching infinite dilution or S1, or this based on this graph, as acetone is near to 0. But for the Lewis-Arundel rule, it applies to the other species approaching purity, or based on this graph, the composition of the acetone is near to 1. That means if we have a binary solution, the composition of the acetone is near to 1. So it's follow the Lewis-Arundel rule. Okay, from the VLE data, you also can obtain another set of the information. Okay, back from the previous topic, we have learned that the excess Gibbs energy over RT equal to the submission of the composition log gamma. So in binary solution, we're going to have two components. From the available data that you have, which are the composition and the log gamma for both components, it gives us the value of GE over RT. And when you divided it to the composition, you can have another set of the data. Okay, these data, which are the log gamma for both components, the excess energy or excess Gibbs energy over RT, and the another latest data is the thermodynamic properties for the liquid phase. By plotting the graph, okay, we plot the graph P over the composition or the mole fraction. We can have this data. Okay, the graph is based on the VLE data, and then when you plot it with the additional information, we can have, okay, from this we can see that this gives the linear line that equal to the linear equation y mx plus c. From this, when we rearrange this data, we can have another equation that correlate to this data. Okay, from this, we can see that from this linear data, or from this linear line, at S1 equal to 0, so we can obtain the value of log gamma at infinite dilution, or you can using this plot graph of log gamma 1. And for this point, it equivalent when you plot the log gamma 2, it gives us the value of log gamma or infinite dilution for component 2. So from this data, it gives another expression that we can further explain about this later. Okay, this is how we obtain the GE over RT equal to 0 when both species whether equal to 0 or 1. And then the slope here, if you can see the slope of the gamma 2 or for the component 2 is always opposite to the slope of the log gamma 1. So from this linear line, it gives us another expression, or we can create the another mathematical expression to determine the Gibbs energy. Another constant that we introduced in determining the excess Gibbs energy, which we denote by A to 1, that means component 2 to 1, and A is 2, 1, 2 for component 1, 2. So rearrange this first expression, we can obtain the A 2, 1 minus A 1, 2 S1 plus A 1, 2. It gives a linear equation. That means when we plot it from the linear line, we can obtain the value of intercept. It represents the A 1, 2, or that constant. We can obtain this constant and another constant from the value of slope. Okay, let's take a break. Okay, from the explanation, differentiate between the Lewis-Arundel rules and Henry's law. What you understand between both laws here. Okay, next we move to the model of Gibbs energy. So since from the previous the data of the VLE, we can obtain the linear line. Access Gibbs energy can be determined from by creating another model from that correlation. Okay, the GERT is function of temperature, pressure, and composition. But for liquid at lower and intermediate pressure, the Gibbs energy over RT is weak function of pressure. Those activity coefficient dependent on the P can be ignored. Hence, the data at constant T is given. So the functional thermodynamic equation or expression can be written like this. Okay, we have the GE over RT as function of G. Okay, thus the data at constant temperature can be written as this expression. Okay, for the binary solution, you can replace these two to obtain this following expression. Or in terms of S1 and S2, we can express it as Raoult crystal. So we can obtain the three component A, B, and C for the variable of the component 1 and 2. Okay, by detailing the Raoult crystal expression. Okay, these are the expression that we discussed previously. Okay, if we have the constant or all the constant is equal to 0 by replacing it, the value of A, B, and C to the 0, we can obtain the GE S1, S2, RT equal to 0. That gives the ideal solution. So we know that the excess energy over RT equal to 0. That means this properties in ideal solution. How about only B and C is equal to 0? That means B and C equal to 0. The remain is A. So GE over S1, S2, RT equal to A. So we can obtain the gamma, okay, when we compare with the ln gamma for each component that we obtained previously, we can obtain the, or it known as the first parameter or one parameter Margus equation. Okay, you can recall this equation from the previous topic in vapor liquid equilibrium. How about only C is equal to 0? Okay, so if the C equal to 0, so we're gonna have two constant. Or you can separate it between the perform this arrangement based on the this arrangement, we can obtain the whether Gibbs energy or excess Gibbs energy over S1, S2, RT or S1, S2 over GERT. So the final equation describing the two parameter Margus equation, or we have Van Low equation. Okay, the difference is the two parameter Margus is based on the A1, 2, or that means the constant is we have A1, 2 and A1, but for the Van Low we have this prime. Or the difference is this is for the Van Low and we have the GES1 S2 RT for the two parameter Margus equation. Okay, we will take a look on the example after this for you to have a deeper understanding on this equation and how to apply this new equation or expression in this topic. Okay, first we move to the one parameter Margus equation. Okay, these are the general equation for one parameter. And then once we rearrange, we can obtain GE over RT equal to A S1, S2. And then multiply it by the mole. We can obtain this value, or this the number of mole or mole composition can be replaced it by the composition. So when we compare with the by using the reconversion of the mole to the composition, it gives the value or the expression of the one parameter Margus equation. So these are the final equation. Okay, how about if we move to the two parameter? Okay, for the two parameter, that means C, D, and so on will be equal to 0. The only available values are A and B. So perform the rearrangement for this equation, and then we can obtain the value. Finally, this is the value for both component in determine the gamma of activity coefficient. Okay, we move to the next is the Van Allen equation. Okay, for the conversion from the Raoult crystal to the Van Allen equation is describing based on this flow. So we have this. Okay, first based on the S1. Okay, since the Van Allen we has the opposite of the Margus equation. For the Margus equation, we have GE over RT times S1, S2. But for the Van Allen, we have the opposite, that composition over the excess Gibbs energy. And then we define the A prime and B prime based on this definition, and then we arrange it, and then after we multiply it by number or mole, and then substitute with the composition. Okay, finally we can summarize the equation of Van Allen, whether using this is for the first component and for the second component. Okay, detail about the Margus equation. If we have the first or the one parameter, we can using it or replace it based on the summability of the excess Gibbs energy. So finally, we can obtain the unknown or the constant of A component 1 to 2 to 1 and 1 to 2 using the linear equation. And then for Van Allen, okay, you can compare it using the based on the summability of the excess Gibbs energy in binary solution. Okay, we have this information, or we can have this expression, and then once you insert it into this Van Allen equation, it gives a linear equation as well to obtain this term, and also the intercept in obtaining the value of A prime for component 1, 2. Okay, I think maybe we can take a look on the example. I hope that you will understand how can we determine the excess Gibbs energy from the VLE data. So the data is given. The first question is determine the parameter for Margus equation that give a linear expression for GE S1 S2 RT using the above data. Okay, from this expression, we can see that this expression is referring to the Margus equation. But if we have S1, S2, GE over RT is referred to the Van Allen equation. So we start with solving the A. So the first is you need to add all the data, the possible data. First, the data is given as S1 and Y1. Those we can obtain the composition of S2 and Y2 from 1 equal to S1 plus S2 and 1 equal to Y1 plus Y2. Second is gamma 1 equal to the, you can use this equation or the equation of modified Raoult's law. So you can obtain the modified Raoult's law before we determine the log gamma 1 and log gamma 2. And then proceed with the GE over RT using this equation. And then you can obtain the excess heat energy over RT, and then you can insert it by divided it into the composition. So this is for the Margus, and this is for the Van Laar. Okay, how can we determine the value of GE based on the slope? So you may plot the graph. So this on the data. So the interested here is the we have this line GE S1 S2 RT, and also the second red one. So the interested equation is both. So we can compare it with the linear equation YMS plus C. So and you can insert into this. Okay, this is for the Margus. Okay, Margus, that means we have this okay, this is for the Margus, and the below expression is for the orange line. And then these are based on the Y, M, S plus C. So insert, you can get the value of A, component 1 to 2. Insert into this. Finally, you can have the value of A to 1. And then for the second also, you need to do the same based on the Y, M, S plus C. So C, you can obtain this value. And then inserting this value into this, and then you can obtain the value of A prime. Okay, this summarize the or provide the guideline of VLE calculation using the modified Raoult's law and the Margus-Van Laar equation. So the Van Laar equation are listed here, and we have learned about the Margus equation. So next we can compare or have the Anton equation in determining the saturation pressure. Okay, we start with the bulk P calculation. Okay, bulk P calculation, that means we need to find the value of P or pressure, and then the S or the S composition is given. So to determine the S2P to saturation, and then from the value of P, you can obtain the value of vapor composition of vapor vessels using the modified Raoult's law. You know that the partial pressure equal to the composition in a liquid times the activity coefficient, and also the saturation pressure. So YI equal to SI gamma I EI saturation over E. And then finally, you can obtain the value of composition in vapor and also the pressure. How about if relate to the DUP? DUP, that means the composition in vapor is given, and you need to find the value of pressure. Okay, so first, since we know that the value of gamma is based on the given pressure, or we can obtain this value from this from the data. However, since the S or the liquid composition is not given, so we need to guess the value, and then after that we can proceed with the value of pressure and also the composition in liquid using the modified Raoult's law. And then we need to calculate the value of gamma from 1. So at the Margus of Van Laar, because the composition of in liquid is not given, that's why we need to guess the value of activity coefficient first, and then after that, when you compare then the calculated and the guess value is similar, you can stop your iteration. Otherwise, you need to proceed with a new iteration. Okay, for the bulk T, we need to find the temperature, and then bulk is the vapor, or bulk is the liquid phase, or the composition in liquid phase is given. So since the we need to find the temperature, so we need to guess the temperature and also only the temperature, because the gamma or activity coefficient can be given if the liquid phase is given. So you can rearrange the Anton equation to obtain the T1 saturation, and the T gas is based on the solubility relation, or T equal to S1 T1 saturation plus S2 T2 saturation. And then from the value of T obtained here, you can insert into Anton equation to obtain the P saturation. So P1 saturation over P2 saturation give the value of alpha. Otherwise, you can obtain the value of P from the solubility relation. Okay, for this method, you're gonna have two ways to solve, whether use it based on this equation or use it based on the alpha. And then after that, you can insert example, you obtain the value of P, insert back into this Anton equation to obtain the value of T. And then you can compare the calculated and gas temperature before we can stop the iteration. And then finally, you can obtain the value of T and also the composition after you finalize the value of P obtained in your calculation. Okay, last we have duty. That means we need to find the temperature and the due. That means the vapor composition or the composition in vapor is given. So if Y is given, so X, you need to find the X. That means is related to the gamma. So you need to guess the value of gamma from the Adamangus of Van Lock equation. And then it's a bit complex comparing the other type of the calculation, because you have two unknown, or you need to guess temperature and the gamma in this type of the calculation. Okay, let's refer to the example. Okay, the following table are TSY. So we have TSY, so we need to define the P, right? Okay, we have two component, acetone and methanol. P is given. Additionally, the following Anton equation. Okay, so we can obtain the value of saturation pressure because the temperature is given. Okay, through the solubility of excess Gibbs energy, Van der equation derive the expression in which is a linear function of S1. So the second question is based on the linear expression obtained in part A, determine the Van der constant using graphical method. So we need to plot the graph. And then at the third is estimate the pressure and vapor composition that is in equilibrium with 70% mole acetone in the liquid. So acetone is component 1, liquid, that means it denotes by S as 1 equal to 0.7 at 100 degrees Celsius. Okay, the last question is determine the temperature and vapor composition at 1 atm for a solution containing 0.5 mole of acetone and 0.5 mole of methanol. So we have, okay, we start to list the Gibbs energy based on the solubility relation, and then we also have the information on the ln gamma for both a compound, and then you may insert this the value of, you may insert the expression of gamma 1 to the solubility, which we know that for the binary system, GE over RT equal to S1 ln gamma 1 plus S2 ln gamma 2. So inserting the expression of ln gamma 1 and 2 into the excess Gibbs energy expression, and then you can obtain the this expression, and then solving this expression by performing a rearrangement, we can have this the negative power of 2, you can divide it, okay, divide by a power of 2 here, and then you can replace this to the new arrangement that you have, and then after that it turns to having this 1 a prime 1 2 times a prime to 1 x1 x2 and a prime to 1 x2 plus a prime 1 2 by cancel out this 1 2 and by cancel out this expression from the above expression that we have, and then it gives the Van Law equation that when we compare to the linear equation, we can have this expression, or it gives us the value of this for the slope, and the other things or the other term is for the intercept. So it proves that the equation of Van Law equation is based on the linear equation y equal to mx plus c. Okay, to answer the question B is determine the Van Law constant from the expression we obtain in A. So the first is you need to have the set of data. So the first is set of data is given VLE, and then we can obtain the saturation pressure from the Anton equation. And then for the ln gamma or the gamma 1, you can obtain it from the modified Raoult's law, or given in this equation, you can insert the value of y, example y1, p you can obtain from p equal to x1 p1 saturation plus x2 P2 saturation, and then from the information or the value of P insert into this equation, you can obtain the composition for the liquid phases and also the saturation pressure for component 1 also you already obtained, and then finally you can obtain another set represent the value of gamma 1 and 2, and then you can proceed to the GERT equal to, based on the summability relation, which is x1 ln gamma 1 plus x2 ln gamma 2, and then another expression you also can obtain from the linear expression that we did previously in A. Okay, the slope from the when plotting the x1 are x1 x2 are T over GE or Van der Waals equation versus x1, we can have a linear slope. So you can obtain the value of A1, A prime 1, 2 and A prime 2, 1 from this relation of linear equation MS plus C. So firstly, you need to determine the value of A and then insert this value to obtain the value of the 2, 1 prime. Okay, the answer is, okay, for the A1, okay, because intercept is 1.4648 equal to 1 over A1 prime. So A1 prime, you can obtain the value is 0.683, and then M equal to 0.3478. 0.3478 equal to A1 prime 1 2 minus A 1 A prime 1 2 A prime 2 1. So insert the value of A1 prime, so 0.63 minus A over A 0.683, and then you can get the value of A21 equal to 0.552. So this is how we obtain the constant from the Van Law equation. Okay, let's continue for the question C. Okay, the question asks us to estimate the pressure and also the vapor composition. That's mean Y that is in equilibrium with the 70% of acetone. So the first step is to extract all the information. X1 equal to 0.7. Those X2 equal to 0.3. The temperature is given or from this information. So the first step is to determine the saturation pressure for both species P1 and P2 saturation. Okay, by inserting the value of temperature, okay, we start with log P1 saturation. We may insert the value 7.11714 minus 1.595. Okay, what is the unit for T? Okay, the unit for T is, please remember that if the temperature in degrees Celsius, the pressure will be in millimeter of the mercury. But if the temperature in Kelvin, that means you can get the saturation pressure in kilopascal. So standardize your unit. Since it doesn't mention about the unit for the pressure, you can use 100 degree instead of convert it into Kelvin. Plus 2. And P2 also can be obtained by inserting the same value of temperature. So log P2 saturation. Okay, if the question is not provided the information about Anton equation, you may refer to your reference table. For each species, it has own expression on own value for the Anton equation A, B, and C. So 1582.271. T is 100 degrees Celsius plus 2. Okay, you can try to solve this. I will share to you the answer is P1 saturation is 2785.68 mmH or mercury, and P2 saturation is 2951 m2 millimeter of mercury. And then the next step is to determine the gamma. We can determine the value of gamma. So C is determine the gamma 1 and gamma 2. How can we determine this? From the equation of, you can use the Var equation, or you can use this equation, Van Laar equation. Okay, next is to determine the gamma using the Van Laar equation. Okay, next we can determine the value of gamma using Van Laar equation. Okay, the equation is not gamma 1 equal to A prime 1 2 plus A prime 1 2 x1 over A prime 2 1 x2 minus, okay, power of minus 2. And can since we already obtained the value of A prime, A1 prime and A2 prime, you can obtain the value of gamma is 1.046. Okay, you may try this to take a look whether you can obtain the same answer like I did. So prime 2 1 1, have A prime 2 1 x2 over A prime 1 2 x1. So the power of minus 2, and then gamma 2 equal to 1.356. And then after that, how can we determine the pressure? So based on the modified Raoult's law, P equal to X1 gamma 1 P1 saturation plus X2 gamma 2 P2 saturation. So you can obtain the value of P is 3118.27 mHg. Okay, next to determine the, the third step is to determine the value of, this is the third step to determine the value of pressure, and then the fourth step is to determine the vapor composition of Y1 equal to, X1 gamma 1 P1 saturation. So to determine the value of Y1, so X1, we insert the value over P. So we already define the value of gamma 1 P1 saturation pressure as well. So just insert the value. S1 is at 0.7. The value of Y1 is 0.65. Or if you need to define the value of second component, so 1 minus 0.65 equal to 0.35. So we can solve this. Okay, next question is determine the value of temperature and vapor composition if the pressure is given. Okay, the liquid fraction also given for both components. Okay, how to solve this to determine the value of temperature? So you can use Anton equation, but you need to perform the iteration. Okay, from the Anton equation, we have this. Maybe we start with it. Okay, the first step is to, what can we do is to determine the T1 saturation and T2 saturation because the pressure is given. So how can we determine the temperature is using the Anton equation. So the T1 saturation equal to, the Anton equation is given. So you just rearrange it to obtain the T1 saturation. Okay, for component 1, 1210,595 over 7.11714 minus log. Okay, what is the pressure? The unit is ATM, so you should change the unit. So P1 ATM equivalent to 760 mmHg. So insert this value to this Anton equation, minus 229.664. You can obtain the value of T1 saturation is 56.1 degrees Celsius. How about for T2 saturation? Okay, the method is the same. Just insert the value of pressure into the Anton equation. Okay, I just write up the value of the expression for Anton equation. So you may try this by your own and let's check the answer together. So minus 239. Okay, maybe I need to make a clear number here. 726 equal to 64.55 degrees Celsius. So how can we determine the T gas? So T gas equal to X1 T1 saturation plus X2 T2 saturation, and the T gas is 60.3 degrees Celsius. So what are the information that you can obtain? So you can proceed to the second information to obtain the insert T gas to determine the value of values of P1 and P2 saturation. So insert this value back to this unknown equation, or log P1 saturation equal to 7111714 minus 1210.595 over 60.3 minus or plus 229.664. So P1 saturation equal to 857.3 millimeter of mercury. Okay, log P2 saturation equal to 8.08097 minus 8271 over 60.3, the same value of temperature, plus 239.726. So P2 saturation is equal to 641.49 mmHg. Okay, what are the information that you can obtain from P1, P2 saturation is the value of P equal to S1. So y, okay, P1 saturation plus S2 gamma to P2 saturation. Since this solution is the non-ideal, or it has the non-similar chemical species. So we need to determine the gamma first. How can we determine it? Using the Van Laar. So determine the gamma 1 and gamma 2. So how can we determine it? By inserting to the Van Laar equation. So ln gamma 1 equal to A12 plus A12 S1 over A prime 21 S2, the power of minus 2. So gamma 1 equal to 1.146. So ln gamma 2 equal to A prime 21 1 minus 1 plus A prime S2 over A12 S1, the power of 2. So you can get the gamma 2 equal to 1.184. So you can determine the value of P. From the equation of P equal to S1 gamma 1 P1 saturation plus S2 gamma 2 P2 saturation. So insert all the value, and the value of P is 641.49 millimeter of mercury. So the next is, how can we determine the calculator of P saturation? So using the correlation of alpha is equal to P1 saturation over P2 saturation. So from this value that you have calculated, P1 and P2, you can obtain the value of alpha is 1.364. Okay, and then from this correlation, you can use the correlation to determine the P1 saturation. Okay, based on this correlation, we know that P equal to S1 lambda 1 P1 saturation plus S2 lambda 2 P2 saturation. So maybe we have S1. You can choose either P1 or P2 saturation. So example, I choose P1 saturation plus S2 lambda 2. Okay, P2 is P1 saturation over alpha. So P1 saturation is X1 gamma 1 plus X2 gamma 2 over alpha. So P1 saturation equal to P over X1 gamma 1 plus X2 gamma 2 over alpha. So you can obtain the value of P1 saturation equal to 754.7 mmHg. So what next we can do is to insert this value to obtain the value of temperature. So the fifth step, I put fifth, 6. The step number 6 is to determine the value of T1 saturation from T1 saturation obtained. So the same method is to be inserted into the unknown equation of 1.595 over 7.11714 minus log 754.7 minus 229.664. It gives you the value of 55.9 degrees Celsius. So you may check. This is the calculated. Okay, let me write up. This is the calculated, and then from the previous is the gas, or the value of gas of temperature. So this is the gas, and then the T1 for the gas and calculator is not similar. So you may proceed to the next iteration. So we can say T1 saturation for calculated is not the same with T1 saturation for gas. So we need to proceed with the next iteration. Okay, the next step 7 is use another gas or T gas. So in this, I am choosing T as T equal to 55.9 degrees Celsius. Or I am just using this value that I obtained to determine another P1 saturation. So you can determine the P1 saturation by inserting into the unknown equation. It gives the value of 754.79 millimeter of mercury. And also at the same time, you can determine the value of P2 saturation is 535.42 millimeter of mercury. Okay, once we obtain the P1 and P2 saturation, we can determine the value of pressure, right? So P equal to S1 lambda 1 P1 saturation plus S1 lambda 1 P2 saturation. So it gives us the value of P. But we can also use another method by using the alpha. Since we already used the alpha, you may use the alpha in determining comparing between the gas and calculated temperature. So P1, P2 saturation. So you can insert this value 792.535.42. So it gives the value of 1.41. So by using this alpha, inserting into P1 saturation, that we obtained, or we already rearranged the equation to obtain the P1 saturation equal to P over S1 gamma 1 plus S2 gamma 2 over alpha, and P1 saturation is equal to 5.47 mmHg. So T1 saturation or the calculated, you can obtain the T1 inserting into the Anton equation. Okay, the Anton is 1.595 over 7.11714 minus log 6 using this 4. So minus 229.664. The value is 56.3 degrees Celsius. So you may compare with this value. So it not the same as well. So you may proceed to the next iteration. So using T equal to 56.3 degrees Celsius. So you follow the same method. So you can get P1 saturation equal to. So I just write up the answer. You may try by your own and you can compare with this calculation. So P2 saturation equal to 544.41 mmHg. And then whereas we have alpha equal to, the alpha is 1.406. And then you can get the another value of P1 saturation using this equation S1, 1 plus S2, 2 over alpha. Okay, P is 7. Okay, the P is 760. Or the given pressure on the question. So by inserting this value of pressure, and then you can get the value of P1 saturation is 764.55 millimeter of mercury. So whereas we can, okay, referring to this, you can determine your T1 saturation. So inserting into this Anton equation, T1 is equal to 56.3 degrees Celsius. So T1 saturation for the calculated equal to T1 saturated for gas. So you may stop your iteration because the value is similar, and then you can use this temperature to determine the P1 and T1 saturation. Okay, the question is to determine the T. So we already determined the T. How about YI or for each composition? So first you need to determine your based on the P. So we can have this value of P equal to YIP S1 gamma 1 P1 saturation. So we can have the value of S1 is 0.7 or 0.5, right? The first given in the case 0.5. So you can get the value of S, okay, given in the question is 0.5. Gamma 1 also is already calculated is 1.146. And then the P1 saturation is, since the temperature is similar, so using this value over P is 760. So the value is 0.576. Okay, Y2 equal to 1 minus 0.576 equal to 0.424. So this is your answer. Okay, I hope that you can try it by your own. Okay, the last topic is local composition model. Okay, within a liquid solution, local composition are different from the overall mixture composition due to the difference in molecular size and intermolecular force. That means in the local composition model, it gonna concern on the interaction between the molecule or the component inside the solution. Okay, the concept of local composition are introduced by G.M. Wilson to represent solution properties, or known as Wilson equation, or it will expand the Margulis and Van Laar equation by having the another term to this equation. Okay, the common local composition model such as NRTL, unique or unique extension known as the unified. Okay, all these model, due to we investigate on the interaction, we gonna use the computer simulation tool to obtain the value, or we can use the equation. This equation can be solved by the computer simulation. So just as introduction to you, how can we apply this equation or related to the local composition model. Okay, for the NRTL has 3 parameters for binary, which are the Gibbs energy. Tau is the based on the interaction for B122 over RT, and then we have also tau 21, which is interaction for B121 over RT. Okay, unique quick, consider the G equal to GE over RT as G equal to GC plus GR. Combination part of the GC is to taken into account on the molecular size. So this is for the molecular size, and then the GR for the forces, molecular forces. Okay, this has similar to the ln gamma, which ln gamma also based on the interaction or the combinatorial and the residual part using the equation that also equivalent to this G, or the term of the G. Okay, unified almost similar to the unique, but inaccurate because the estimation of activity coefficient based on the contribution of the various group making the molecules of the solution. Okay, for your assignment proof and to test your understanding, maybe you can list or differentiate between the Margulis and Van Laar equation. You may refer to the previous slide that I already explained about the between both equation. Okay, so for the next topic, we will move to the second part on this chapter, discussing about the property change of the mixer because we already compare between the ideal solution. So how can they, based on the access property, how that the property change for the mixing, what is the thermodynamic properties or the relevant thermodynamic properties in the mixing process. So by end of this slide, I think that will end my presentation today. And thank you for your attention. I see you for the next topic. Okay, bye.